All right, so chapter 9, we're going to be learning about some organic chemistry. And that may seem pretty difficult, but we're going to be going over the basics of what's involved with organic chemistry and the types of functional groups that we see in organic chemistry. And you've probably seen molecules with structures of molecules before, and probably wonder what they mean. So we're going to learn a little bit about that today. So just to give you a fun little introduction, now this is the reaction for creating meth. Now, the way you make meth is actually from cold medicine, from Sudafed. So pseudoephedrine, that's what this is right here, cold medicine. And it's very analogous to a thing called ephedrine. Maybe you've heard of that. So that's a drug too. But so Sudafed, where you can get over the counter, but it's limited on how much you can get because they know you could make reactions and make meth with it if you're an advanced chemist. But the idea here is that this is what organic compounds look like. This is what some of them could look like. You have it's basically a bunch of shapes, right? And we'll learn what these shapes mean. Basically, the corners, these little vertices, they're carbon atoms. And then obviously we see an OH or an NH that represents oxygen and hydrogen, nitrogen and hydrogen. And then a different, there's this dashed line, which kind of tells you the three-dimensional structure. And the dashed line means that this is pointing away from you. This wedged line means it's pointing towards you, etc. But the idea is that you can go from cold medicine, or really you can create anything in organic chemistry. So you can go from cold medicine and you can do a reduction reaction and you can make meth. So that's crazy. The reason why is because organic chemistry involves a lot of very finely regulated structural thing. The structure, two-dimensional and three-dimensional structure, means a lot. So here's Sudafed, the cold medicine. Here is the same exact compound. This one, this pseudoephedrine minus. Same exact compound, but the only difference is their enantiomers. We're going to learn about what that means, but we're not going to go crazy on it because it's a pretty difficult concept. But basically, that means they're mirror images of each other. So whereas this OH group right here on the left, Sudafed, is pointed away from us and the wedge is pointing towards us, this minus Sudafed is the opposite, meaning this OH is pointing towards us and the wedge is now away from us. So all that means is the three-dimensional structure is pointed opposite and you get a completely different biological outcome. So where one's a cold medicine, one is not on the market. It's not really used for any drug, but Pfizer does have a patent for it. I'm not sure why. Maybe they use it as a precursor to making other drugs. I'm sure Pfizer makes their own line of Sudafed, so they probably use it in their reactions. But they basically have the same exact structure, written the same exact way, but just two bonds are flipped in terms of their three-dimensional structure, and you have completely different outcomes. Then, if you do a reduction reaction, which basically reduction means, when we learned about this in class, oxidation reduction. So a reduction reaction is you're getting rid of the oxygens. So what they do is they get rid of that OH group and you reduce it. If you do that in both cases, the Sudafed, if you do a reduction reaction on a Sudafed, you get meth. You get actually methamphetamine. And it's called D-methamphetamine. That's the one that is harmful. And it's a very potent drug that can ruin people's lives. Then the mirror image of that, meaning if you take the other Sudafed, the minus Sudafed, which is not a drug, and you do the same reduction reaction to it, you get L-methamphetamine. So you have D-methamphetamine and L-methamphetamine. So L-methamphetamine is not nervous system active. It doesn't really affect your nervous system at all. And it makes you drink a lot of Merlot. Basically, it doesn't really do anything. I think it just makes you, I don't know. It's not, maybe it gets you buzzed a little bit. I'm not exactly sure, but it's not a life-ruining drug. Let's put it that way. And the only difference is one bond. That's the point here. So the only difference is this wedge, and at the end of this wedge, if you're wondering like, oh, what does that mean? So that means there's a CH3 group on the end of that. So you can basically look at this as, me get the pen. Wait, what just happened? You can look at this as CH3. CH3. So you can look at this as the CH3 group, or it's called a methyl group, is facing the other way. So the idea here is that one bond difference can create a completely different biological activity. And we see that with a lot of drugs, that their isomer partner is not active at all. So that's really interesting. And the reason why, I'm sure you're wondering, is, oh, why is that the case biologically? Well, it's because where these drugs bind into our body is different proteins and neurons, and then they really affect different biological processes. Now, to affect these biological processes at high potency, you have to have an exact three-dimensional structure that is specific to an enzyme or a protein or a cell or some receptor or something of interest. So let's say you have this D-methamphetamine, and it binds very nicely into this pocket. There's a pocket. Let's say this is an enzyme, right? So let's say it's an enzyme. It binds very nicely into that enzyme. If you rotate this bond from this way to the opposite direction, it's not going to bind as nicely into that pocket. So if I were to draw the same pocket over here, right? Let's say this is facing the other way. It's not going to bind as nicely. And just from that one bond not binding as nicely, it can reduce all of the activity. So that's why the three-dimensional structure is extremely important when it comes to drugs binding to a receptor or anything in the body that can make the drug have an outcome. So this stuff is this is why organic chemistry is very important for developing these drugs, and to know like the very specific three-dimensional and two-dimensional structural mechanisms, because they vary and that changes a lot. So as you can see here. Okay, any questions on that? Because it's a pretty interesting topic. No? All right, moving on. So organic chemistry, what it is, it's the chemistry of hydrocarbons and their derivatives. So there are tens of millions of known chemical compounds. You can make an infinite amount of compounds. And over 95% of them are based on carbon, of these organic compounds. And here's examples. Here's propanol, 2-methyl-2-butanol. We'll learn about what all these mean. Basically, you can connect a bunch of carbons and hydrogens, and also oxygens and nitrogens. So the main four elements that are in organic compounds and organic chemistry, I call them CHE. So carbon, hydrogen, oxygen, and nitrogen. That is what 99% of your body is made out of, just these three elements. Every amino acid is made of these elements. Only one of them two of them have sulfur. But really 99% of everything in your body is just from these four elements. And you can create all these different types of proteins and really every kind of cell, everything in your body that's different, every different tissue type, just out of these four elements. And it's all based in organic chemistry. So that's very interesting. So we have carbon. Carbon is the thing that bonds all of these elements together. So that's the backbone. Now we are carbon-based life forms. So that means our chains of all of our molecules in our body are based on carbon. That's why in order to make drugs, we need to have carbon-based drugs, which is organic drugs, to intermingle with our organic body. So here's what carbon looks. This is not what our body looks like. This is just solid carbon. But if you put it into different like carbon, these are different carbon-based structures. So these are different alcohols. But our body has some of these, but very, very low concentrations. And just if you're wondering, the alcohols that are the ones that get you drunk are ethanol. So ethanol looks like this. It's got 2 carbons, it's got an OH group, and it's got a bunch of hydrogens. So like something like moonshine is just pure ethanol. And then methanol, which is just with one of these hydrogens, that's toxic and you can get blind from it. It's really bad. So that's another example of how one carbon could change the whole dynamic of the compound and what it does to your body. But anyway, so the hydrocarbons are a hallmark in organic chemistry, and they're the simplest organic compound. And as their name implies, they're composed completely of hydrogen and carbon. So here's something that you do have to know is that at least the 4 carbon numbers, right? So what that means is if you have 1 carbon, we call it methane, or simply the prefix meth. And no, that has no relation to methamphetamine. And the reason why they call methamphetamine is because it has a methyl group. It has methyl involved. So the word actually comes from 1 carbon being in one of the side chains. So here, I'll show you why. So here's methamphetamine, and this is the meth group right here, methyl. The CH3 is 1 carbon, and the rest is the amphetamine. So that's where they come with. They come up with a name. All right. So you have two carbons. You have F. So it goes meth and an F. So meth is 1 carbon. F is 2 carbons. Then prop. Prop is 3 carbons. I know it says propane, and they all say ane here, but ane corresponds to being an alkane, which we'll go over in the next slide of what that means. That basically just means you're single bonded with all carbons throughout the whole structure. And then the next one you have is butane. So basically the prefix is but, or it actually pronounced bute. So not butane, butane. That's with 4. So these 4 prefixes are important for organic chemistry because we're going to be using them to name different things. And we're going to learn very basic naming schemes, but there are those 4. So I perhaps might give you these on the exam, or I'm not give you them, give you questions on them, and you have to know them. So the alkanes are the simplest forms of hydrocarbons that only contain single bonds. And they're also called saturated hydrocarbons. So maybe you've heard of saturated fats, unsaturated fats. This really follows the same premise, where when you have a saturated hydrocarbon, that means the hydrocarbon is saturated with hydrogens. Now, what that means is it has the most amount of hydrogens that the carbon atoms can possibly harbor. So, for example, this is ethane right here, right? You have CH, or you have C2H6. These are carbons, these are the hydrogens. So you have all the hydrogen. You have 6 hydrogens. Now, this is ethane. I'll write this down, ethane. If I were to make this a unsaturated, this is saturated, meaning is the most carbons it could possibly have. If I were to make this unsaturated, what I can do is replace 2 of the hydrogens and make a double bond between the carbon. And instead of having 3 hydrogens to each carbon, only have 2. This is called ethene. And this is called an unsaturated hydrocarbon. So meaning it can still take in more hydrogens if you get rid of this double bond. And now this is where our knowledge of Lewis structures and the electron dot structures comes into play a little bit, meaning we have to know that carbon has 4 bonds maximum. Because in order to do this, we have to know that, all right, in the ethane's case, carbon's 4 bonds are 1, 2, 3, and 4. But if you remove the hydrogen, you have to have that 4th bond, and we can put it in between both the carbons and make it a double bond. So this is just, there's a transition from a saturated to an unsaturated hydrocarbon. So it's just important to understand for now. So the alkanes with the ANES, they are the single bonded. So if you have ane, that means single bond. And they usually follow this formula. Don't really worry about the formula too much. Basically, what this means is the number of carbons that the ethane or the alkane has, the number of hydrogens that corresponds to it will be 2n plus 2. So if you have propane, so propane is C3, and then it would be H, you put the 3 in there, it would be H8. So that's propane. So if you have like a propane grill, that's what propane is. And then you have butane. Maybe you've heard of butane tanks. You have octane, right? Octane you've heard of probably. So octane is C8, and then H, you would put it in that formula, you'd get 18. That's what octane is. So these are all forms of alkanes. And they're all, alkanes are synonymous with saturated hydrocarbons. Yeah, so here's our example, or here's our definition. So alkanes, they are consisted of the number, they have the A and E ending, and they have the prefix corresponding to how many carbons they have. So meth is 1, eth is 2, prop is 3, but is 4. And then after but, it gets easier. So that's why I said these 4 are really important, because after that, it gets easier. It gets pent, hex, hept, oct, non, dec. So that basically corresponds to the shapes, like your pentagon, hexagon, etc. But there's no such thing as a propagon or a butagon. So that's why these terms are organic chemistry specific. So that's why it's important to know them. And then there's a way of representing these structures as ball and stick models. So that's what we've been seeing so far. And that's just to show you what that is. If you have usually smaller white atoms, those are hydrogens. And then usually the ones that are bigger, and they're usually brown or black or a darker color, those are carbon, or dark gray, those are carbons. And then you have oxygens, usually could be blue or red or usually different color. And then nitrogens could also be a different color. And you can tell which one's which based on the number of bonds they have. So something we know from electron dot structures is that hydrogens only like to partake in one bond. So that's why, and they're very small. So that's why these are hydrogens. And then carbons like to partake in 4. So that's why these are carbons, because every one of these gray ones partakes in 4 bonds. And then we can condense this structure. So there is an important thing I want you to understand here is how to go from a condensed structure to a written out structure. So not the ball and you don't have to draw the balls and sticks, but there's a way to write this 2-dimensionally that also makes sense. So if I have propane CH3, CH2, CH3, I would expect you to do this. Know that the carbons are bound to each other, and then you're just going to stick the remaining hydrogens on. Like this. Yeah, so I would expect you to go from here to here. So let's do some examples on that. And basically with any one of these alkanes, we know that the carbons are bound to each other. So it's never going to be, so if you see this equation or see this formula, the first thing you might think is, oh, it goes C, H, 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 whatever, and just like it's written. That's not true. That can't be the case, right? Because of what we learned about electron dot structures. So let's do some examples here. We'll do butane. So butane is CH3, CH2, CH2, CH3. So we're going to write our 4 carbons that are all in a row, and they're all bound to each other. And then we're just going to add in the remaining hydrogens. So on each of the ends, there's 3 hydrogens. And then in every middle carbon, there's 2 hydrogens. And the way we know this is because that's how many hydrogens it takes to make 4 hydrogens on each carbon. Or sorry, to make 4 bonds on each carbon. Because you'd have, on the ends, you'd have 3 hydrogens and then 1 bond that's carbon-carbon. And in the middle the middle carbons, you'd have 2 hydrogens and then 2 bonds that are carbon-carbon. Okay, so then we have another thing. Are there any questions on that first? No? All right. All right, then we have another column here that says number of possible isomers. So what is an isomer? Now, let's look at the next slide to figure that out. An isomer is something, or they're compounds that have the same molecular formula but different structure. So this is a very important definition. They have the same formula but different structures. So kind of like we saw for the meth before, where if you switch one of the bonds, it becomes a completely different drug. That is a type of isomer. But the isomers we're going to be getting good at in terms of making the isomers is structural isomers. So here's an example of butane. This is butane. So you have 1, 2, 3, 4 carbons is called butane. And this one is the same exact formula. So let's count these up. We have 4 carbons, so C4. How many H's? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have H10. So that's butane. We know that. Then this one, it's a little bit different. If you look at the connections, the first butane has 1 connected to 2, connected to 3, connected to 4. This butane, if you try to do that, has 1, 2, 3. Oh, where's 4? The fourth one is actually connected to the second one. So you have 1 carbon that's in the middle that's connected to the other 3 carbons. If you do the formula for that one, you have C4, H1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's still C4H10, but the arrangement is different. So we're basically moving around the carbons, and you can do that, and you can still maintain the same formula. Now this, and the way to differentiate between the two, this one's called butane, and this one's called isobutane. And the reason why we use the prefix iso, and you're not going to have to know this specifically, but the reason why we use iso is to say isolation, kind of like in basketball, right? Iso. So it's like one-on-one kind of thing. So it's like you have 1 carbon in the middle that's kind of bound to everything else. So it's iso. So everything else is isolated. So that's what that means. And they're the same structure. So isomers. So a good question that I will give on, I think, the homework and generally on the exam, something that's good to know is if I were to give you a structure such as, let's do propane, or let's do, propane, there's no isomers. There's only one. Let's do pentane. So write pentane. If I were to give you a question for pentane, draw me 2 isomers. So, all right, pentane. Pent means 5. Ane means it's saturated, meaning there's no double bonds, which we'll learn what happens when double bonds come into play, but it's just all single bonds and there's 5 carbons. All right, so let's draw 1. We have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, all connected by bonds. And then we just put in the hydrogens. And then for every middle carbon, we have 2 hydrogens. Like that. Okay. So now a very easy way to answer the question, which is draw another isomer, is all you can do is take the carbon from the end and put it somewhere in the middle. Let's say we put it on this one. That would give you an isomer. So for example, I'm going to draw this in the condensed form just to save space. You'd have this carbon, then you'd have this carbon. Now this middle carbon, we're going to put the end carbon onto it. So it would actually look like this. We have to get rid of one of these H's, and then we have to put it on the end. We're actually replacing this CH3 group and putting it on the end here, and then putting this carbon on the end over there, and we're doing this. So that's what it would look like. And there's multiple ways to write isomers, because for something like pentane, if we look at over here, pentane has 3 isomers. So we drew 2 of them already. So that's an example. And if you do the formula just to check yourself, check your work, you have C5, and an H, you have 3, 5, 6, 9, 12. C5H12. And this one is also C5H12. So you know that it's the same formula. Okay, any questions on that? Of how to draw the isomer. So I would expect you to do something similar of, let's say, pentane or hexane. It wouldn't be too difficult. I wouldn't give you decane and say draw all the isomers, because there's 75 of them. So that would be insane. No? All right, moving on. All right, so there's some of the alkanes, and here's some of the properties of them, such as, and if you go from the top, methane, all the way down to, you have more 18, 19, or 20. This is 20 carbons. You see what happens to the melting point, boiling point, and density. So the melting point is going to increase. What does that mean? That means it requires more energy to make them melt. That makes sense, right? Because they're bigger. You have more atoms in there. You're going to have more bonds to break and more intermolecular forces to break. So such as like water is held together pretty tightly. That's why the melting point of water is considered to be high. I mean, 0 is considered to be high. But and because the reason why is because you need a lot of energy to break apart the intermolecular forces between the water molecules. So that's the melting point. Then the boiling point also increases. Why? Because, okay, you need more energy. The bigger the element, or sorry, the bigger the molecule is, the more energy you're going to need to break apart those bonds in a liquid to make them into a gaseous form, to give them enough freedom to become a gas. And also the density increases as you make larger molecules, because since the atoms are so small, they approximately take up the same amount of space, but there's more atoms in that space, meaning they get heavier in the same amount of volume. So the molar mass increases, which means the density will increase. So that's how that works. Basically, the bigger the hydrocarbon is, the bigger its boiling point, bigger its melting point, and the bigger its density, the larger its density. So then you can have some fun with these, and you can kind of make different structures, and you can make any kind of, really anything you can imagine, different shapes. Like we saw it with the meth example, where you have these hexagons here. These are called aromatic rings. We'll learn about in a second, but that's why these double bonds are here. But you can also make just plain cyclic hydrocarbons, which are ring compounds. Now, something important to mention with these, you can make any shape you want. This is called cyclopropane. It's basically a triangle. And you have the remaining hydrogens are on the carbons to make 4 bonds of each carbon. So here's a question that I'm going to give to, or whoever wants to answer it can answer it, is if I have cyclopropane, is it an isomer, meaning is it the same exact formula as regular propane? So propane, I'll draw a propane. You have 3 carbons in a row. Like that. So here's the question anyone can answer if they want. Are these isomers, meaning do they have the same structure, or sorry, the same formula, but different structure? Oh, we have an answer. Let's see. Oh, it's okay. So anybody, are they isomers? Meaning the same structure, or different structure, same formula. We have one answer. I'm not sure if that's right.
No.
Good. No, they're not. So the reason why they're not is because if you do the formula for each of these propanes, this is regular propane, and this is cyclopropane. So let's write cyclo. This propane formula is C3H8. Now this one is C3, but how many hydrogens? 1, 2, 3, 4, 5, 6. It's H6. And the reason why they're not isomers is because you have this extra bond, this extra carbon-carbon bond. Whereas regular propane has 2 carbon-carbon bonds. This would be 1, this would be 2. The cyclo has to have a third one to make them a cyclo, to make it a ring. So where this third bond would be, normally you'd have 2 extra hydrogens, but you have to remove those 2 hydrogens to make this carbon-carbon bond, which makes them not identical. Even though they're both types of propane, they're not identical propane. So that's important to understand, that when you have a cyclohydrocarbon, it's completely different than a regular hydrocarbon. They're not the same formula or the same structure. So, and here's some examples of those. We are this cyclopropane, this is cyclohexane, and now we can get into our next thing, which you see that cyclohexane has 6 carbons all in a ring, in a hexagon. And all you did here was you removed 2 of these hydrogens and replaced a double bond in there to make sure the carbons all have 4 bonds. And what that makes is cyclohexene. The only difference is that one letter. So what does that one letter mean? And here's exactly what it is. That means you have an alkene. So the naming scheme of this is actually very easy. If you change the ending, kind of like we did for ionic, you change the ending, it kind of means something different for the structure. So alkene, what that means is a hydrocarbon that contains a double bond. Oh, sorry, it's not a good line. So double bond, very important. So an alkene is double bond. And the formula generally is CnH2n. Don't really worry about that. So it's usually the same prefix as how many carbons, followed by an ene. So this is ethylene. So it's the simplest alkene. So you have double bond right there. Then you have one called alkynes with a Y. The only difference here is a Y. And what that means is a hydrocarbon that contains a triple bond. And the general formula is this. Don't really worry about that. And they have the suffix -ine. This is ethylene, known as acetylene. Now, let's summarize this. So you have alkane, so meaning the A is a single bond. You have an alkene, which is the E, double bond. And then you have an alkyne, which is the Y, triple bond. So easy way to remember it is the alphabet. The further you go in the alphabet, the more bonds. A, alkane, single bond, simple. Alkene, it's further in the alphabet, double bond. Alkyne, towards the end of the alphabet, more complex, triple bond. So easy way to remember it is just in the order of the alphabet, single, double, triple. So kind of questions that I would be expecting you to answer on the exam or homeworks would be, if I give you a bunch of structures, which of the following is an alkene? You'd look for the one with the double bond. Or which of the following is an alkane? I'd look for the one with the single bond. Or draw an alkyne, for example. So all you'd have to do, if I said draw an alkyne, doesn't matter what kind you draw. Let's say you do 3 carbons, propine. That's a thing. You do C, 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 and then one of them just has a triple, but not all of them, just one of them has a triple bond, and it would be like this. That's propine. And you see how all the carbons need to have 4 bonds, even if it's a triple bond here, and that's true. So you have this carbon has 4 bonds, triple and then the single. This one has triple and the single, and this one has all singles. Yeah, so it's alkene. Sorry if it's a little sloppy. So these are K. These are K. My K's look like H's here. Okay, so yeah, any questions on that? So just be distinguishing between those. And Stephanie, our exam is in 2 weeks. I talked about that in the beginning of class. Okay, so the next thing we're going to talk about is aromatic hydrocarbons. Now, you've probably heard of this before, the word aroma, or maybe you've heard of aromatic. If those of you who are into fragrances or different perfumes and things, they're called aromatics, which means they have an aroma, which means they smell. They could be either smell really good or they could smell really bad, depending on what type of aromatic it is. So what does aromatic mean? What makes a compound have this smell or make it aromatic? And the answer to that is really, people know that aromatics have a smell, but nobody really knows why they correspond to a smell. I think because of our nose can detect aromatics because they can be harmful, usually harmful and like toxic, but making aromatics that are making perfumes that are not toxic, that's a goal of modern chemistry, and one of the fragrance chemistry. Fragrance chemistry is actually a big thing you can go into. A lot of my friends that were in undergrad with me are now into different fragrance companies, and they do different organic chemistry for them. So that's interesting. A lot of money in that. So the thing that makes them have this smell or have this aromatic, makes them aromatic, is double bonds. So this is basically almost like cyclohexane. It's very similar. Now, if we went back to cyclohexene over here, where you have the double bond, it's kind of like cyclohexene, but you have 3 double bonds. You have 1, you have 2, and you have 3, and they're alternating. That's the key component, is when you have something that's aromatic, you have alternating double bonds. That's very important for aromatics. Now, this gives the structure a lot of different properties. 1, it begins to smell. 2, it gives them an absorbance property, meaning, and fluorescence too. So which means that this compound can now absorb light. So for example, if you take propane gas, or let's see if we can think of a better example. Yeah, propane gas, why not? Take propane gas and you shine a light through it. No, or let's say you look at, you can see methane gas, right? You can't see it. Let's say you have a propane tank. If you turn the knob a little bit, you hear it, right? You don't see the gas. You maybe see like how it moves the air around it, and because maybe it's hot or something, but you don't see the actual gas. The reason why is because the gas doesn't absorb any light. But for these aromatics, it's a little bit different. The gas, or if they were gases, they do absorb light. And what we can do is we can detect if they're there based on absorbance and fluorescence. So because they fluoresce. And the reason why they fluoresce is because these bonds, these double bonds, since they're alternating, are constantly moving. So it's called electron delocalization. We're not going to have to worry about that. But basically what that means is the electrons are constantly jumping. And what those electrons constantly jumping, so double bonds are constantly jumping from here to here, and they all like move like what's that game? Musical chairs. Yeah. So they move like musical chairs. And that happens extremely fast. So when that happens so fast, it kind of makes electrons in a kind of like a loop. And the electrons are going around and around and around and around and around constantly. So it makes kind of like an electron force field in the middle. And that electron force field in the middle can actually absorb light, and it can refluoresce it. So that's why aromatics are very different than other compounds, or very different from other hydrocarbons, is that they can absorb light. And we take advantage, as organic chemists, we take advantage of this. So if we want a compound most of our drugs, so most drugs that are made, and here's an example, here's all your different methamphetamines and things, but I would say 90%, if not more, of drugs that are made and put on the market have an aromatic ring to it. So here's an example of that aromatic ring, and they all have it. And we can use that aromatic ring when we are making the compounds to detect if our compound is actually there. And we can use it there's different techniques we can use to detect that compound based on if it's aromatic or not. So everything that's not aromatic, we would not see, and everything that is aromatic and what we're looking for, what we would see. So it just so happens that things in our body respond well if we make drugs that contain aromatics. So it makes it easier for us to detect. But anyway, so it's kind of like a cyclohexane, but it's not. And this one's called butane, or not butane, sorry, benzene. Whoops. Benzene. Benzene is the key, the hallmark aromatic hydrocarbon. So it's like a hexane, so it's cyclohexane, kind of 6 carbons, and then you have alternating double bonds. That's a benzene. So there are many different types of aromatic hydrocarbons. So benzene is the main one, where it's just the 6-membered ring with, and the way to draw it, you got the circle in the middle. And the reason why I did it over here, so the double bonds that are alternating, they're alternating so fast that the electrons are kind of delocalized in the middle. They're kind of spinning around, like I said. That's why you can draw just a circle in the middle. And if you're drawing this shorthand, it makes it a little bit easier. So here are just some, you don't have to memorize any of these, but here's just some examples of different aromatic hydrocarbons. And there's a bunch of different other ones that don't just contain hydrogen and carbon. Some of them contain nitrogen, oxygen, and things like that. So caffeine is similar. So caffeine has aromatic to it also. So just to show you what caffeine looks like. It's in coffee, of course. So caffeine looks something like this. It's got double bond oxygens in there. So it's got, so I'll show you this example. Let's see, this is nitrogen. This one's a nitrogen. Yeah, so that's basically what caffeine looks like. And the thing that's aromatic here is this ring, is this pentagon. It's aromatic because you have an alternating double bond here. So it's not, the whole thing isn't aromatic. If it was, you'd have a double bond here and here as well. But just this ring is aromatic. But that's enough for it to absorb light. So caffeine is aromatic as well. Anyway, so there we go. There's some aromatics. Okay, so now we can talk about something else that is also something you could do to hydrocarbons is you can, instead of having hydrogen on them, such as propane and where everything's a hydrogen, you can put chlorine on it or fluorine on it. And you can make chlorinated hydrocarbons. So you can have dichloromethane, which all that means is kind of breaking into prefixes into the name. Dichloro, 2 chlorines, methane. So let's do that. So you have methane, which is just, we know it's 1 carbon. So this is why we're going over these, because I want to show you how the name of the compound can tell you exactly what it means. So before this class today, if you saw dichloromethane, you would have no idea what that means, maybe. But if you see it now, methane, oh, you know what that means? That should be a green light in your head of, oh, 1 carbon, or a light bulb in your head. 1 carbon. Chloro, you know what that means? Chlorine, Cl. Di means 2. 2 Cls in a thing that has 1 carbon. So this is methane, the thing that has 1 carbon. If you put 2 chlorines in there, you'd have Cl, and the rest of them are just hydrogens. So that's dichloromethane. So it's used as paint remover and just a general solvent. Then you can have trichloromethane, otherwise known as chloroform. So this will knock you out. And you can have basically the same concept, trichloro, 3 chlorines in a methane. So, and then also you have tetrachloromethane, or that tetrachloromethane is known as carbon tetrachloride. So you can have those different names. Does that make sense? And there's a plethora of names. So if I were to give you something maybe complicated as dichloromethane, that's something that if I gave you answer choices, you should be able to figure out. So let me give you that example real quick. So difluoromethane. So that would be 2 chlorines, 2 fluorines, methane. So, you know, carbon, it's got 2 fluorines in it, and it's got 2 chlorines in it, like that. So something like that would be fair game. And generally, this goes perfectly into the chlorofluorohydrocarbons, or the chlorofluorocarbons, called CFCs. Now, CFCs, there's a reason why we have them on a separate slide. It's because they're important in climate change. So in 1996, we detected that because of the CFC emissions from the chemical plants, because the CFCs were a large byproduct. They're very toxic to the environment and a huge byproduct in a lot of chemical and manufacturing processes. Now, it was detected that because of these CFCs, they actually reduced ozone to O2 and I think it was O2, HCl, and some other compound. And we found out that it was actually depleting the ozone. So these CFCs were responsible for depleting the ozone. So I'll just put depleted ozone. So maybe some of you have heard growing up in school and maybe you've heard in your science classes that the ozone layer, that's something that's important, that prevents radiation from coming in to the Earth's atmosphere. And it's protecting us, but because of our pollution and everything, the ozone is actually disappearing. This is not true anymore. It's in the textbooks. It's in all the textbooks, but it's not true. So it used to be true because of these CFCs. Right after we figured that out in 1996, we banned CFCs. So 1996, banned CFCs because we knew that they depleted the ozone. After banning CFCs, 20 years later, in 2016, we have a completely restored ozone layer. So no one talks about that. Everyone always talks about it's news. You know how bad news is. News is always like negative, but nobody talks about the positive. And with climate change is a huge issue now, or it's always really been. But lately, in the last, I don't know, 5 to 10 years, people have been talking about it more. And no one talks about our positives. So a lot of countries are making huge strides in cleaning up the environment, such as the U.S. and China, which correspond to a lot of the initial pollution in the first place. And something that's a good achievement is that, or a big achievement, is that we restored the ozone layer. So this is very important. It cures cancer, in essence. It lowers the percentage of cancer and mutations of all life on Earth because you have less radiation and solar flares, solar radiation coming into our atmosphere. So that's hugely important and a very big milestone in modern industrial times. So functional groups. So now the last thing we're going to cover, and this really is the remaining half of the chapter, is these things called functional groups. So functional groups are things you're going to have to kind of memorize. They're not too difficult. They're very similar to each other. And there's ways to memorize them. But what they are is atoms or groups of atoms that are attached to a hydrocarbon skeleton. And they give the compound characteristics and properties. Now, what does that mean? So that means if you could basically make modifications and attachments to hydrocarbons. And we did that already with the chlorinated hydrocarbons and the fluorinated hydrocarbons. Those are considered functional groups. And we made attachments. So you can make different types of attachments. You can make something into an alcohol. So here, for example, let's talk about ethane and ethanol. So ethane looks like this. It's got 2 carbons and it's got 6 hydrogens. Now, if you have a bunch of ethane, you're like, I want to get drunk. What are you going to do? Change it into ethanol. Put on a functional group, something that makes it alcoholic. And this is exactly what ethanol looks like. So it's got 2 carbons, and then instead of one of the H's, you replace that H with an OH. This is called the alcohol functional group. So that's an example of how a functional group can change the overall behavior of a compound. So that's one of them. So here's the list of all the functional groups. And we already know several of them. So the first one, alkane, is very simple. It's just the normal carbon structure. Then we know you can modify it by making a double bond called an alkene. Then you can modify it again by making a triple bond called an alkyne. Then we just learned another one. You can add an OH onto it and make an alcohol. And there's a bunch of other ones we're going to cover. So in this general formula, what that means is you see this letter R. So R is not an element. R is not like argon or something. R is not an element. R represents any group. It represents anything. So any additional hydrocarbon, and then you can replace that with R. So if I have an alcohol and I do, let's see, this is my structure. It's got some crazy stuff to it. It's got a benzene ring in there. It's got looks like a little birdhouse. It's got like a bunch of stuff in there, whatever, a bunch of weird structures. Then at the end of it, it has OH. The R group is everything else. So R just represents, you could think of it as random. You could think of it as just an R group, a random group of any other hydrocarbon. But the idea is that whatever is attached to that R group, in this case OH, is considered the functional group. That makes it have that specific function. Okay, so there's a bunch of them. There's ether, which is this is just an alcohol, but it's in the middle. Then you can have aldehyde, and then ketone, carboxylic acid, ester, amine, amide. But we'll go through these systematically. First one's alkyl. So another name for these alkanes is an alkyl group. So we've talked about these already. So yeah, propyl, butane, right? But if you make these different groups that are attached to different structures, you call them, instead of propane, you call them propyl groups. So yeah, but that's not too important. We already learned about these. Then you have alcohol. So alcohols, you're basically just adding an OH on the end of it. And you're moving one hydrogen and making an OH. So there's methanol, ethanol, 1-propanol. And the reason why it's called 1-propanol instead of just propanol is because this OH can go in different places. It doesn't have to go on the last carbon. It can go in the middle carbon. So let's draw the difference between 1-propanol and 2-propanol. So 1-propanol looks like this. You have your 3 carbons, and then you have an OH on the end, or the OH can be in the beginning. It doesn't matter. It's the same structure. So if I drew the OH over here on the left side instead of on the right, it would be the identical structure because you could just flip it and it's the same thing. Now, but 2-propanol, that's not the case. So you have your 3 carbons, or sorry, yeah, 3 carbons, your 3 hydrogens. And in the middle, you have an OH and an H. So this is 2-propanol over here, and 1-propanol is right there. And you see the difference. They're not identical. They're the same formula, but they're not identical. So these would be kind of isomers of each other, but they'd be, completely different structures. You'd have the OH in a different place. So that's that. Okay, so there's methanol, there's ethanol. Here's like the ball and stick model. I said that the oxygens will show up in red. So those are the oxygens. This is an OH group right here. And here's the other 2 carbons. And then what you can do is if you add more alcohols, it can change the function as well. So you have ethylene glycol, which is ethanol, but if you add another OH. So if you add an OH to the other carbon, then you get ethylene glycol. And then you can have propylene glycol, which you're adding more carbons to that structure. And then you can have glycerol, which is a type of alcohol where you're adding, it's like an oil, glycerol. It's like kind of viscous. And that's if you have propane, but every one of those propane carbons you replace with an OH and you get glycerol. So basically, if you add more oxygens, it doesn't make you more drunk in essence, but it could change the behavior of the compound and change its properties. So then if you add, a lot of these is going to be adding things we already know to other things we already know. So if you take this alcohol group and you add it to a aromatic, you get a phenol. So a phenol is an aromatic group with hydroxyl. So hydroxyl is another word for alcohol. So that's all it means. So I'm going to draw up here. It's good for note taking. So where's my pen? The OH is alcohol and also hydroxyl group. They're the same thing. So if you have a hydroxyl attached to an aromatic ring, you get a phenol. So here's different types of phenols, and they're used in antiseptics in general. Okay, moving forward, the next functional group is called an ether. So an ether. People say ether sometimes, but it's ether. So ether it's kind of like an alcohol. So alcohol is like this, right? But instead of having the H on the end, we're like, nah, let's connect something else, something that's different, right? Another R group. That's exactly what it is. It's like an oxygen. It's like an alcohol that's sandwiched in between two hydrocarbons. So here is an example of that. You have diethyl ether. So you have an ether. This is the ether. Diethyl. Remember we learned that F means 2 carbons. Diethyl, 2 times 2 carbons. So here's one of those ethyls. Here's another one of those ethyls. So you have diethyl 1 and 2 ether. So an ether is something that has an oxygen in the middle, like that. That's diethyl ether. You can have dimethyl ether. You can have propyl ethyl ether. You can have really any combination you want. So these names, there's infinite possibilities. So here's how you make an ether, or here's what you can do with ethers. You get a ethylene oxide, which is an ether. So it's got the O bound to other things, and then you add it to water, and you can make ethylene glycol. But not really too important. So then you have another type of functional group, which is called, there's actually several of these. Aldehydes and ketones are just 2 of them. And what these groups consist of is a carbonyl group. So carbonyl, you see that word carbonyl? That means a carbon double bound or double bonded to an oxygen. So the name for carbon double bonded to an oxygen is called a carbonyl. There are several functional groups that contain carbonyls. One of them is an aldehyde. An aldehyde is a carbonyl, but with one of the sides being a hydrogen and the other side being random group. Then you have a ketone, which is effectively the same thing as just a carbonyl with just 2 random R groups on each side. They could be the same, they could be different, doesn't matter. But they can't be hydrogen. If one of them is hydrogen, it's automatically an aldehyde. So that's another key thing. The R groups have to be something else. They can't be just hydrogen. Or they can't be just oxygen, because that's something else as well. So does that make sense? So right now you have so a carbonyl itself is not a name of a functional group. It's just there's functional groups that contain it. So the more specific name, if I were to give you something like this on an exam, let's say you had C double bonded O, and then you had CH3, whatever, and something else, you had CH2, blah, 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 blah. And I asked you, what is the name of this functional group? The answer would not be carbonyl. The name would be ketone. It's a ketone because you have, this is an R group on the right side, R group on the left side. That's it. If I replace this one with just hydrogen, let me erase. Can I even erase? Where's my eraser? It's not showing up. All right, whatever. So if I replace this with just hydrogen, then it would be an aldehyde. It wouldn't be a carbonyl anymore. It wouldn't be a carbonyl at all. It would be an aldehyde because you have the carbonyl group with a hydrogen, meaning, and then a random group on the right side, meaning it's an aldehyde. Okay, so here's some balls and stick models of these. So here is a carbonyl group, but this is an aldehyde, the simplest aldehyde. And then here is another aldehyde. And then here's a ketone. So then we can make another functional group from this carbonyl. So let's say we took a ketone, it's not ketone, by the way, it's ketone. You take a ketone, which is R with a double bond, C double bond O, and then another R group. This is a ketone. You take a ketone, and instead of one of these R groups, you're like, I'll put in an alcohol. Get rid of that, put in alcohol. You get carboxylic acid. So a carboxylic acid is the main determinant in figuring out if an organic compound is acidic. The more of these carboxylic acids it has, the more acidic it is. So that's what we mean by, we get back to the definition of functional groups. All of these groups have a specific function. For the carboxylic acid's case, it makes it more acidic. For the alcohol's case, it makes it more alcoholic, and it could make it more polar. For ketones and aldehydes, it makes them more polar as well and moves their electron density. But so this is the one that's more apparent in terms of what it does. It just makes the acid more acidic, or makes the organic compound more acidic. That's what carboxylic acid does. And then what you can do is you can always attach things onto each other, and you can say that take this carboxylic acid and let's plug it onto an aromatic benzene, and you get benzoic acid, which is a weak acid. So the key thing is, remember we talked about strong and weak acids and bases? These organic compounds, even when they're acidic, are going to be weak acids. They're very weak because they're not strong. But a better explanation is because they're going to have hydrogens and not hydrogen. They're going to have a lot of carbons on them. So that generally makes them weaker in terms of their ability to deprotonate, meaning this H would come off when it becomes in solution. So if this deprotonates, that means this oxygen is going to be negative and you're going to have H plus. So that is how an acid would dissociate. But this would happen very weakly. This would be a weak interaction, unlike HCl, which happens instantaneously. So then what if you're like, all right, I'll take this carboxylic acid and I'll do the same concept we did before. So remember we had an alcohol and we said, all right, let's take off the hydrogen and put something random on there. We went from alcohol to ether. So now let's do the same thing. We'll take carboxylic acid, we'll get rid of the hydrogen, and we'll put random group. We call this an ester. So an ester is something that looks like this. And you can react an acid with an alcohol to make an ester. What would happen is the hydrogen from the alcohol, we'll make water with the alcohol from here, and then whatever's remaining from the alcohol, which is the oxygen with the R group, will bind to the carbon, making an ester. So ester is like a carboxylic acid, but you're removing the H and putting in an R group, meaning something random. So that's a good way to think about it. So they're all interrelated. And esters generally have a pleasant odor. So a lot of the odors that we have are esters. So some of them are aromatic, such as these bottom ones are aromatic, but some of these aren't aromatic, and they still have a nice flavor and odor. So apple, pineapple, pear, a lot of these fruit flavors have to do with esters. So that's pretty cool. So we're not going to worry about the naming of esters, but what you can do is if you have the 08 ending, butanoate, that means you have an ester on the end of it. So methyl butanoate, that means you have butane, that means you have 3 of the 4 carbons are on one side, then you have the ester group, and then you have the remaining 4th carbon. You could have dimethyl propanoate, which means you have, dimethyl butanoate, which means you have one methyl on one side, or you have ethyl. You have ethyl butanoate, which means this this ester group will be in the middle. So you have 2 carbons and ester, then the other 2 carbons. So something else that's important to mention is to go from this extended structure to a 2D structure. So we know how to do this already with the CH3, CH2, CH3. But once you get to this, how would you write that? Now, I'll just give you the answer. So let's write this whole compound out, methylbutanoate. So you have CH3, another carbon, CH2. Third carbon would be CH2. Now the fourth carbon, or sorry, wait. I did one too many carbons. Get rid of this. Start over. So you have that second carbon, third carbon. Now this third carbon, or you do have 4 carbons. Oh, yeah. So you have your third. I was right. You have your third carbon, then your fourth carbon for the butanoate part, and then your methyl. So your fourth carbon will look like this, and then you'll have the 2 oxygens. It's not going to be OO. It'll be one of them will be double bound, one of them will be single, and then you'll have CH3. So that's what the methyl butanoate looks like. You can have ethyl butanoate, or you can have ethyl. If you add ethyl butanoate, all you can do is add another carbon to that. You can have ethyl propanoate, meaning I will take this ester group and I'll put it in the middle and then move this carbon over. So there's a lot of options. I know maybe it's too much. I'm just going on a tangent, but there's a lot of options here with the naming. Okay, so there's 2 more. The first one is, and they both have to do with nitrogen now. So now we're going to introduce nitrogen into the equation. Before we had just carbon and hydrogen, then we introduced oxygen in some of the functional groups. Now we're going to talk about nitrogen. So nitrogen is the other one of those key organic elements. Remember we talked about CHON being our 4 key organic elements: carbon, nitrogen, oxygen, nitrogen. Sorry, carbon, hydrogen, not oxygen, nitrogen. So the first one is an amine. So amine. So an amine is a derivative of ammonia. So what that means is ammonia is NH3. If you have an NH something, maybe it's NH1, NH2, NH3, they are amines. So if I take, there's different types of amines. This one's called a primary amine. This one's called a secondary. This one's called a tertiary. So a primary amine has almost NH3. So let's take ammonia. We'll get rid of one of the hydrogens and put on an R group. That's a primary amine. A secondary amine, take ammonia, take off 2 hydrogens, put 2 R groups. A tertiary amine, take off 3 hydrogens, make 3 R groups. So basically, wherever you have a nitrogen in an organic compound, you're probably going to have some kind of amine or amide group going on. So amine is the first one. Basically, if you see a hydrogen in your structure and it's bound to either one thing, it's called primary, 2, it's secondary, and 3 different random R groups, it's tertiary. So then the last one is called, or here's some examples of amines. The last one's called an amide. So an amide is, all right, let's take the concept of, we talked about carbonyls, meaning the aldehydes, ketones, carboxylic acid, and esters. Take that concept and we will throw on a nitrogen to the carbonyl. Once we throw on a nitrogen to the carbonyl, we can have all these different possibilities. These are called amides. So there's a difference between amine and amide. Both have nitrogen, but the amine is simply just a nitrogen. An amide is the carbonyl attached to a nitrogen. That's important. Okay, cool. So is there any questions on that or on any of these? Okay, so before we finish up, I just want to show you the chart again. Now that we learned about these, here we go. So here's that chart. Remember, we talked about alkenes, alkynes, meaning double bond and triple bond. Alcohols are the OH. Let's take away the H and put on another functional group, or sorry, another random group. You get an ether. Then you can put in a carbonyl group in there, and you get the simplest carbonyl is an aldehyde. So you have the C double bond O with an H. And these usually occur at the end of molecules because really after this, you can't go any further. You can't add any more. So it would be at the end. Then if you take off this H and put on a random R group, you get a ketone. If you kind of mush a aldehyde or a ketone and an alcohol together, you get a carboxylic acid. If you take the carboxylic acid and take the hydrogen off of it and put on a random group, you get an ester. If you just have a nitrogen just randomly in the middle of the carbon structure, you have an amine. If you have a carbonyl, like let's say you get a ketone, or here's a better pattern. If you get a carboxylic acid, instead of the OH, you add a nitrogen and you replace them, you get an amide. So the reason why I'm saying it like this is because that's an easier way to memorize these things instead of just trying to identify them just from memory. If you have associations built in, such as like I said, alcohol is an OH. If you mix an alcohol and a ketone, it would make a carboxylic acid. If you take an amine and a ketone, it makes an amide. So things like that. If you take the alcohol, take off the hydrogen, it makes an ether. If you take a carboxylic acid, take off the hydrogen, add something else, you get an ester.